Hi, welcome back, and let's get on with another video. This is going to be a short one, like 15 or 20 minutes. We'll be covering, last time we discussed buffer pools and what are buffer pools and how they serve as a cache for your disk pages to be brought into memory and serve as an access point for your execution engine to read data off of them. So a buffer pool is basically structured like frames, like you have different frames and you can bring in disk pages into the frames. And then you can hand back the pointers back to the execution engine which requested the page originally. So we also took an analogy between a comparison between mmap and buffer pools and why mmaps are bad. And both both of the cases they just try to attempt like they make an attempt at reading pages from the disk and mapping it such that your process can use it, your database process can use it. But then we also saw that how mmap, when you give control to the mmap, you lose control over when you're writing to disk, and the operating system can do various things in the background which might not be desirable by your database system. And it might be the case that you end up losing some data for some of the users. So we saw this, and then we discussed that what databases used to use mmap, and then they moved out of it. Then we also saw that what issues there are with mmap, like there's transaction safety, IO stalls, that your operating system might page fault in the background, but to your thread, it is just another wait that you're doing on a system call. But in the background, the page of that particular file might not be fetched, and the operating system might be just alluding to you the fact that it is fetching the page right now, uh, and it is like to your thread, some useful work is being done. Then we have performance issues that if when you are context switching, you might have TLB shootdowns where you'll have to rebuild the TLB cache for the operating system page tables. So the bottom line is that buffer pools serve as a cache, and if we take a step back and we think about RAM also. What is RAM? RAM is basically a cache for your programs, where your program lives and where they store their data. So your programs usually live in on the disk, and you bring those programs into memory, and then your RAM serves as a temporary storage for the lifetime of that program. So similarly, a buffer pool is nothing but it is a cache for your pages on disk. So, like any other storage, buffer pool is limited. It does not have infinite storage, and you will run out of frames very soon, given that your data might be in gigabytes. So, how do you maintain a efficient algorithm that swaps out pages, the pages you are not using, and just keeps in the pages that are hot and the ones that you're using? So, how do you design an efficient algorithm? So, we'll discuss those algorithms now. And we'll start with the LRU, the least recently used, and then we'll work our way up to the clock, and then we'll also look at least frequently used LFU, and then we'll look at approximate LRU. Then we'll look at approximate LRUK, which MySQL uses, and in the end, we'll look at ARC. That is something adaptive replacement scheme, I guess. No, I don't know what it spells out, but I'll also have to study it more. I'm not covering that arc thing in this lecture because I am not very familiar with it, and I will have to study upon it to deliver something on that particular topic. So let's start with least recently used. So this is the like an ancient algorithm. Uh, like whenever you talk about caches, the first this is not the very first thing that would pop up into your mind. Most probably FIFA would come up first in, first out, like a stack. But that's a like CS 101 when you ask your students that what is the basic cache replacement algorithm that you can think of, then most of them will apply FIFO or this LRU. So what LRU concept is simple that you maintain a timestamp of when the page is last accessed, and when the time comes for an eviction, you just choose the page that has been the that that was accessed the longest before. So I did not put it well, but the page with the oldest timestamp. Yeah, that was a better word there. So the page with the oldest timestamp, let's say you're accessing pages. So we'll go through the slides. So Andy has done this has created these beautiful slides where if I scroll, then basically I'll be doing a walkthrough of the process of the LRU. So let's say we are maintaining this list. It's a doubly linked list and it's a list of pages. So whenever I access a page, I take that page and I append it to the beginning of the list. That is how I make sure that that page gets its timestamp updated, that it has been accessed very recently. So eventually, what will happen is the page that has been not been accessed recently will just move to the end of the list. So originally, let's say our LRU structure is like this. We have pages in a linked list, and then someone tries to access a page. Let's say some query comes up and accesses page one. So this is query Q1 and it is accessing page one. So what I will do is I will move page one to the head of the linked list. So now page one is at the head, then page zero goes in the second place, and page two is in the third place as it was before. So now the time comes for an eviction. The eviction algorithm runs that I don't have space in my buffer pool and I need to free up something. So my algorithm runs and it decides that it will feed off of page that is on the end of the list, on the tail. So what I do is I just traverse to the tail, or I can maintain a different pointer to the tail as well. And but I will have to update that tail pointer every time I move the list. So yeah, as Andy says that you don't have free lunches in computer science, you have to make trade-offs. So yeah, you take some whatever is in the tail and you evict that particular thing. So that is least recently used. As simple as that. Either you can maintain a linked list, which is very simple. You just maintain a list and you just append to you move the pages to the head and you maintain a tail pointer and you update it as you reorganize your linked list. Or you can maintain timestamps. You can maintain a hash table and for every page you can maintain timestamps, but that's not a very good idea. Thinking of that, let's say your eviction algorithm runs and you you will not have any order in that. So what you will have to do is you'll have to iterate through all the hashes in the hash table and compare the timestamps. So hash table is not ordered. So what you'll have to do is have to scan all the keys and you'll have to look up the timestamps. You'll have to compare them, and that's basically an O of N operation in memory because this thing is happening in memory itself. So the second algorithm we are discussing is the clock algorithm. This is what Linux uses, the Unix kernel. Uh, they use multi-hand clocks, but uh, this basic clock algorithm is the building block of what they use. So the Linux kernel, while they are deciding that what pages need to swap out to the disk and what I need pages should I not swap out to disk, they use a clock algorithm. So clock algorithm is very simple. What you do is you maintain a reference bit. This reference bit is different from what we discussed in the buffer pool pins, that how many people are referencing this. So in that case, a page was being referenced by multiple queries. So you update that reference count that one query is accessing that or two queries are accessing that page. So that particular reference count is different from this particular bit. So don't get confused. What this reference bit does is you maintain a bit for every page, and let's say initially you have all the references to zero. And wait, yes. So initially, what you'll do is initially you'll have your empty buffer pool. I have this empty buffer pool, and I'm bringing pages in. Just assume that these are frames. I'm bringing page 1, page 2, page 3, page 4, page 5. So assume that this is my buffer pool. It's a linear block of memory. Uh, and just assume that this particular thing has been mapped to a circular clock like this, just for demonstration purposes. This has nothing to do with how it is represented in memory or in disk. It's just a slight representation of what we are discussing. So what will happen is initially when I bring pages into memory, all the reference bit will be set to 1. Move it here. Every reference bit will be set to 1. Now there will be a hand in between. What is a hand? But it could be it depends on you how you emulate this hand. You might run a for loop, you might iterate over all the pages. You can do various things actually. Uh, yeah. So when you start rotating this hand, what you do is you go to each page. You Yes. So you go to each page, you check if its reference bit is set to 1, and if it is set to 1, you turn it to 0, and you move on to the next page. We move on, we move on, and we move on. So currently there was nothing to evict. But what will happen in the next time is when I actually started with the wrong analogy there. Okay, let's restart for this. Let's restart this clock algorithm. Okay. So initially, everything is in memory. Okay, pages are brought into memory into the buffer pool, and I'm not very sure that what is the initial bit there, because if I set all the bits to 0, then ideally all my pages are, yes, that would make sense. If I set my initial bits to 0, then it would make all my pages equally likely to be evicted, rather than setting all my reference bits to 1, because in that case, if all my pages are set to 1 and the algorithm cannot find any page to evict, then it will run out of memory. It will give you an OM error. So initially all the reference bits are set to 1. So let's say a query comes along, q1 comes along, and it references page 1. This is what is shown in the next slide, that a query comes along and it references page 1. As soon as it references page 1, I turn this reference bit to 1. That this is just a bit. It's not a byte. You cannot increment this. So you're just turning that flipping that bit from 0 to 1 as soon as a query accesses it. Now let's say that query is running. It is running in background, and another process comes in, the eviction process, the process or the thread which is responsible for eviction from the buffer pool. That comes in and it starts its clock algorithm, and it looks at this page that its reference bit is set to 1. Now, if the reference bit is set to 1, it means that some query recently accessed it. So what I'll do is I'll turn this reference bit to 0 and I'll move on. I'll move on to the next page. So this slide shows that the clock algorithm has set the reference bit to 0, and now it's going to move out to the next page. Now, in the next page, the reference bit is already 0. What that means is that the last time I came across this circular ring, uh, this reference bit, I did not set this reference bit to 0. It is already 0. So it might be the case that I came across this page last time and it was 1, and I had set it to 0, and between that time interval where I ran again, so assume that this is my first instance where this is T1 where my first clock algorithm ran, and this is T2 where my second algorithm is running. So assume that my page has been set, my bit has been set to 0 by this first T1. And by the time I come to T2, if it is still 0, that means that no query has accessed it between this time interval. I hope that makes sense. So I can evict this. This is a candidate for eviction. Now you can choose multiple candidates also, but Usually, you pick a candidate and you just evict it and you stop your clock there. So this slide shows that the reference bit was already set to 0 and you just throw this page out. So that page has been swapped. It was page 2 and now we have some page 5 that has been brought into memory. And we discussed that why its reference bit is initially set to 0 because no query has accessed it yet. Now, let's say my database is standing still now, no queries running, and my clock algorithm again runs in. That maybe I'm doing vacuum or I'm doing some garbage collection that some sort of JVM is running and it's asking that what memory you can free up or something like some maintenance process, let's say. And you start your clock algorithm again. You look at page 1 and you see that the reference bit is again 0. So what that means is that no query has accessed it between the time interval that I ran before and now I'm running. So this page is available for eviction because no query has referenced it between that time interval. So I will just throw this page out and replace it with something else. So this is clock algorithm. You maintain a hand and the queries come along. They change the reference bit to 1. Your hand comes along. It sees all the ones, sets them to 0. And as soon as it finds a 0, which is already 0, which it has not set to 1 in the same cycle, it throws that page out and replaces it with something that it needs. So it is very simple. The clock and the LRUs, they are very simple. Now, there is something, a phenomenon known as a sequential flooding. What happens in a sequential flooding is you run a sequential scan on a table. Let's say I want to select all on I run a select star on the whole table without any indexes. So what my database system will do, it will find out where is my root page. It will go along depending on if I'm doing a heap-based file storage or a tree-based file storage. It will go to my root page, start scanning along the nodes. Let's assume that it's a tree-based storage. It will start from the root of the B tree, then it will jump down and I don't think we have covered B trees though. But it will start from the top root node. It will jump down, traverse the tree, and then it will just sequentially rip across the end of the B tree to get all the tuples. What, but what that will do is it will bring in pages which are just to be accessed once for that one select statement. But it might flush out pages which are important to you. But due to that one select star, you had to evict those pages out. So assume that you have a hot page, you are writing to it, you're reading through it, and it is in memory. It is live and loaded, and it's like you are writing to it, so your multiple workers are writing, multiple workers are reading. Then some query comes along in the same scenario, some query comes along and it's decided that it wants to do a select star on your database. So what that will do, assuming that your database is huge, you will go to the disk, ask for a ton of pages, you get those pages into memory in your buffer pool, and it might happen that your buffer pool might get filled up with all of those pages, all the sequential scan pages that you're doing. And in that process, you're touching these pages once, but the page which is hot might starve. That queries might not be touching that because you're running this expensive query here and you're touching a lot of pages. So these pages might be able to evict this hot page, and then your majority queries, which were using this hot page, might have to struggle a bit. So that is a phenomenon known as sequential flooding, that you just keep on touching pages sequentially, and that uh, pollutes the buffer pool. So we'll read it through. A query performs a sequential scan that reads every page and in a table one or more times. And this pollutes the buffer pool with pages that are read once and then never again. So that's what I was talking about. That one query comes up and it replaces your hot pages. Okay, so there is this statement. I might have to go, but we'll cover this last statement here. So, if there is the statement that OLAP workloads use most recently used uh, as a best page to evict. Why is that? Like, you might wanna, if you're watching this, you might wanna pause and think about it. That why would analytical systems use most recently used pages as a best choice? I'll give you 10 seconds. Anyways, okay. So why is that the case? Because it's an analytical system. You are querying data. So you might be running some analytics and you might query some data, but it is very highly unlikely that you will be requesting the same data again. Once you have run it, you have brought in some page into memory. That is the most recent page, and the most recent page you have calculated some statistic on some application level or on some human level, and then you will never use that page again. So the most frequently used pages will be on disk, but it is highly likely that the most recent pages you are bringing into memory, you will never be able, you are never going to use those pages again because you have extracted the data, unless you are running like some query which is requesting the same page again and again. But usually in an OLAP workload, once you read the data on an application level, you calculate some statistic and then you don't need that page. So the most recently used page is the best choice for eviction. It's more of a use case based scenario that your use cases might differ and not everybody can relate to this statement. But yeah, yes, I also believe that it's heavily based on use cases that uh, it depends what kind of analytics you're doing at the end of the day. And yeah, so we'll stop here. We covered clock, we covered LRU, we covered what is sequential flooding, and we covered that why sequential flooding, why clock and LRU are, we did not cover that, that why clock and LRU are susceptible to sequential flooding. Should we cover that? Let's cover that quickly. So let's look at the sequential flooding slide. So what you're doing is, let's say a query is coming along and it wants to do a select star. It wants to do a sequential scan on your page. You don't have indexes. Just assume that there are no indexes out of the box. So you touch pages. You Then there is another query that shows up. It wants to do an average on some column that called as val from A. So page 0 is brought into memory. Then page 1 and 2 are brought into memory. Now let's see. Select star from A where ID is equals to 1. That query is running. Okay, that's touching the page 0. That might not touch page 1. That might not touch page 2. But let's say page 0, 1, and 2 are brought into memory by any of these queries. Now query 2 will try to mm, no, 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 no. Why are color coded differently? Q2, Q2, Q1. This will be Q3, I think. Yep, it will be Q3. Hmm. Hmm. Yes, this will be Q3. That's it. Okay. Apart from that, let's start over it again, and we'll have to cover this quickly, but I'll come back to it in the next video also. I was not clear what was happening exactly, but let's say Q1 comes along and it is doing select star from where ID is equals to 1, no indexes, and it has brought a bunch of pages into memory, 0, 1, and 2. There is another query that is doing a select average from val from A, and it is going along all the pages and sequentially reading and calculating that value. Now, query 2 might cause a problem because it is sequentially touching all those pages. So let's say Q2 wants to bring page 3 at the end of it. Page 3 is trying to be brought into memory, and let's say that this ID lives on page 0 itself, page 0. So Q2 wants to bring in page 3, and now it will tell the eviction algorithm that I need a spot. So what the eviction algorithm will do that what the eviction algorithm will do, it will find the best candidate, and given that these pages are currently brought into memory, all of them are equally likely to be evicted. So Q2, sorry, the evictor will just push out page 0 back, and it will bring page 3 in. So page 0 is replaced by page 3, page 1 is there, page 2 is there. But now this particular Q1 is again fired. Let's say it is a hot query we were talking about, and it is fired again. This is Q3. So Q3 comes along on the same level, on the same semantics that I want to select star from where ID is equals to 1. And what happened was page 0 was swapped out, which actually contained the data. There are no indexes here, and there is no query level caching here, nothing. So what will happen is that you'll have to again go and fetch page 0 and assume that you're doing this over and over again. Your sequential queries are bringing in pages which are replacing your actually useful pages, the page 0 that contained ID 1. So that what we were talking about, that your hot pages might get replaced when you do this sequential scan and bring all the pages of the table into the memory. So yeah, we'll discuss more about this in the last thing, but yeah, let's see. Thank you for watching, if anybody's watching.